Hi, this is my presentation. I'm Amy Williams, and my presentation is on Chapter 14, Problem 1. Consider a map with less than 12 faces and with the degree of each vertex at least 3. Show that there is a face bounded by 4 or fewer edges. And then the second part will be without using the 4-color theorem, show that such a map can be colored in 4 colors. So for the first part, Euler's formula stated that faces plus vertices minus edges equals 2. And then we're going to look at when we have 2 times the number of edges should be greater than 3 times the number of vertices. So we're going to start with our graph. It has less than 12 faces, and each vertex has a degree of 3 or greater. Using the formula, we can say that the number, if we rearrange it, we can say the number of vertices is equal to the number of edges minus the number of faces plus 2. Since G is planar, then the following is true. So if we look through this equation, we are given that the number of edges should be less than or equal to 3 times the number of the vertices minus 6. In place of the vertices, we're going to replace it with 2 plus the number of edges minus the number of faces. And as we do that, we'll go through and we'll distribute the 3. So then we're down to the number of edges is less than or equal to 6 plus 3 times edges minus 3 times faces minus 6. The 6's cancel, so we have number of edges is less than or equal to 3 times the number of edges minus 3 times the number of faces. Move the 3 edges over, we have negative 2 times edges is less than or equal to negative 3 faces. So when we get rid of the negative, we have 2 times the number of edges should be greater than or equal to 3 times the number of faces, which is what we had on the previous slide. Okay, so we know each edge has 2 vertices, so the sum of all the vertices is 2 times the number of edges. And the part we just looked at a minute ago, so 2 times the number of edges has to be greater than 3 times the number of vertices because each vertex is of a degree 3 or higher. Okay, so what if it was a degree 5? Because we're looking at saying that there has to be one that's 4 or less. So what if they're only 5 or more? So if we go through and look at 5 or more, when we go through all the math, we get down to 2 times the number of edges is greater than or equal to 5 times the number of faces. So the problem arises in the fact that if we have 11 faces, we have to have at least 16.5 edges, so 17 edges. So when we substitute in the number of edges and the number of faces, we get the inequality that 49.5 is greater than 55, which is false. Therefore, there must be a vertex whose degree is 4 or less. That should be 4 or less. Okay, now we want to go, we want to talk about the second part. Okay, so I'm going to pull up my whiteboard. Okay, so the second part said, if we had 11 faces, prove they're going to be colored with 4 colors. Let me read that to make sure I'm reading that right. Without using the 4-color theorem, show that such a map can be colored in 4 colors. Okay, so we're gonna help my whiteboard work when I do this. So I'm looking at this and I'm like, okay, so we have 11 because we have this outside one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11. So let's say that the outside one gets the color A. See if I can. Okay, that means none of these can be A. Maybe I'll put it over here. So we could have A, color A, color B, color C. Guess I'll do this one. Color D. There's probably a way to change these colors, and I just don't know. But we're going to do this with dots. Okay, so none of these can be A. Okay, so let's say that we make this one B. Okay, then we could make, if that's B, that's A. A can't be any of these, so this could be C, which means this could be C. All right. Well, if that's C, this could be, why is that a different color? B. This could be B, or, there it is. I knew I could change them. I didn't mean to. Is this still my B? That's B. This could be B. This could be C. This still can't be A, so it's going to have to be D. And then we go back and we're like, okay, so this can't be B or C, so it could be A. This can't be A, and it can't be B, and it can't be C, so this one has to be D. So this one is going to have to be A. So with 11 vases, we just colored it, and we ended up with 4 colors. Okay, so the question is, what though if I got rid of one of the edges? See if I can remember how to get rid of an edge. If I don't want to add a line. Put that away. I don't want to select the text. Select this line. Trash. There. So we just got rid of one of the edges, right? So that means that we have to recolor. Okay, so this is A, but now this is being touched by A. So we're going to get rid of that A. Get rid of that. Okay, so this can't be A anymore. It can't be B or D, but it can be C. So we still can color it in 4 colors as we go down. So we can do this as we go down. We can erase sides and get rid of faces and still keep going. Okay, so let's see. Yeah, I just did it. Now I don't know how I did it. No, undo that. I do know how to undo. Okay, let's get back here. What if I do right there? Delete that one. I got rid of B too. Okay, so A once again is all the way around the outside. So we said that could be B, that could be C, that could be B. This cannot be A anymore. We're going to delete him. And so we're going to... So if he can't be A, he can be D. All right. This one has to become A now. And then this one, oops, come back, can be B. So we still can do them in 4 colors. Get rid of another. So we can get rid of another. So now if I get rid of this one, we're going to delete him. Then technically, we're going to delete him too. So now we have an A. And so this time there's nobody on the outside touched by A, so he's okay. So as we go down, using the what's called the greedy color, we can show that we can always do this all the way down in 4 colors or less. Thank you.